Imagine a night sky so crowded with stars that you can't even trace the familiar shapes of constellations. Now, picture not just one or two stars orbiting each other, but seven locked in an intricate dance of gravity, light, and chaos. This isn't science fiction. It's the reality of septuple star systems, some of the rarest and most baffling cosmic arrangements we've ever discovered. These systems don't just defy our expectations, they shatter them, rewriting the rules of how stars form, survive, and interact in ways that leave even the most seasoned astronomers stunned. What makes these systems so extraordinary? Think about the delicate balance required to keep just two stars orbiting each other smoothly. Now multiply that complexity by 7. Stars of different sizes, temperatures, and ages, all bound together in a gravitational puzzle that shouldn't, by all conventional logic, even exist. Yet here they are, scattered across the cosmos like celestial miracles, each one a laboratory of cosmic weirdness. From stars that eclipse each other in bizarre, unpredictable patterns to ones that steal matter from their siblings, septuple systems are treasure troves of the unexplained, challenging everything we thought we knew about stellar evolution. This journey isn't just about cataloging strange phenomena, it's about peering into the extremes of nature itself. Over the next few minutes, we'll unravel 30 of the most mind-bending discoveries from these systems, each one more astonishing than the last. How do stars this crowded avoid catastrophic collisions? Why do some of them burn brighter and die younger than their solitary counterparts? And what secrets do they hold about the origins of our own solar system? Strap in, because we're about to venture into one of the universe's best-kept secrets, where the rules of physics don't just bend, they sometimes break entirely. The first confirmed septuple star system wasn't just a scientific breakthrough, it was a cosmic wake-up call. Hidden within the constellation Orion, astronomers stumbled upon a celestial ensemble so complex it rewrote the textbooks. Using a combination of high-powered telescopes and spectroscopy, scientists detected not one, not two, but 7 stars locked in a gravitational ballet so precise, it defied all existing models of star formation. The key to uncovering this system, light, by analyzing subtle shifts in brightness and color as the stars eclipsed and tugged at one another, researchers pieced together a puzzle no one expected to solve. What made this discovery so shocking was the sheer improbability of it. Conventional wisdom suggested that systems with more than 3 stars where unstable gravity would inevitably fling excess stars into space or trigger catastrophic collisions. Yet here was a septuple system, not just surviving but thriving, with stars of wildly different sizes and temperatures orbiting in a delicate hierarchical dance. The primary stars formed a tight inner group, while the outer stars whirled around them in wider, slower orbits, a configuration that shouldn't have lasted more than a few million years before collapsing into chaos. But the real bombshell, this system, known as Say the Name If Provided or Let Me Know If You'd Like a Placeholder, wasn't young. Its stars showed signs of advanced age, meaning this improbable arrangement had somehow endured for billions of years. That longevity forced astronomers to rethink everything they knew about stellar dynamics. If such a system could exist, what other cosmic rules were waiting to be broken? The discovery didn't just add a new curiosity to the galaxy's catalog, it cracked open the door to a universe far stranger and more unpredictable than we'd ever imagined. If you thought the orbits in our solar system were complex, wait until you hear how septuple star systems laugh at predictability. In a typical binary system, 2 stars follow neat, elliptical paths around their shared center of gravity, elegant and predictable. But throw 7 stars into the mix and suddenly, gravity becomes a frenzied game of cosmic pinball. The result, orbits that zigzag, loop unpredictably, and sometimes even switch partners in gravitational dances that leave astronomers scratching their heads. Take the system known as a RSBC, where 3 inner stars whirl around each other at breakneck speeds while 4 outer stars trace erratic, ever-changing paths. Observations reveal that one of the outer stars doesn't just orbit. It gets yanked inward by the trio's gravity, slingshots around them, and then gets flung back out like a celestial boomerang. In another system, 2 stars pirouette so close that their mutual gravity distorts their shapes, creating tidal bulges that further destabilize their orbits. These aren't minor wobbles, entire trajectories can flip in just a few thousand years, a blink of an eye in cosmic terms. Why does this happen? It all comes down to gravitational chaos. With so many massive bodies tugging at one another, tiny differences in starting positions or velocities snowball into wildly divergent outcomes. Even a slight nudge from one star can send another careening off on a completely new path, making long-term orbit predictions nearly impossible. Unlike the clockwork precision of our solar system, where planets follow paths we can calculate centuries in advance, septuple systems are more like a high-stakes game of space roulette, where every spin of the cosmic wheel reshuffles the rules. The most mind-boggling part, some of these systems shouldn't even be stable enough to last. Computer simulations show that most configurations of 7 stars should either collapse into collisions or eject members into the void within a few million years. Yet, against all odds, we've found systems where this chaos has persisted for billions of years. It's as if the stars have found some precarious balance, a fragile truce in their gravitational warfare, one that defies our best models and hints at hidden laws of physics we're only beginning to glimpse. One of the most baffling features of septuple star systems is how they defy the cosmic rulebook when it comes to size. In most stellar families, stars tend to be relatively similar in mass like siblings close in age. But in these crowded systems, it's not uncommon to find a behemoth supergiant sharing an orbit with a tiny dwarf star, a pairing so mismatched it's like a grizzly bear adopting a house cat. These extreme size differences shouldn't happen under normal star-forming conditions, yet they're weirdly common in septuple systems, and the reasons behind this anomaly are as fascinating as they are unexpected. Take the system TKL7, where a blue supergiant, a star so massive it could swallow our Sun 100 times over, orbits alongside a red dwarf barely larger than Jupiter. How does such a lopsided partnership even form? The answer lies in the chaotic nurseries where stars are born. Unlike single stars or binaries, which emerge from relatively orderly clouds of gas, septuple systems often arise in dense, turbulent regions where multiple collapsing gas pockets collide and merge. In this cosmic free-for-all, some pockets accumulate far more material, birthing supergiants, while others get starved, producing runts. Gravity then binds them together in a makeshift family, regardless of their size disparities. But the strangeness doesn't stop there. These mismatched stars don't just coexist, they actively influence each other's fates. The supergiant's intense radiation can strip away the dwarf's atmosphere, leaving it even smaller, while the dwarf's gravity might siphon material from its massive sibling, creating erratic outbursts of energy. In some cases, the smaller stars act like cosmic parasites, stealing matter until they ignite violent flares or even trigger supernova prematurely. It's a stellar soap opera where the players are anything but equal, and the drama unfolds over billions of years. What's truly mind-bending is that these systems shouldn't last. Conventional models predict that the gravitational tug of war between such wildly different masses would tear them apart. Yet, against all odds, they persist, a testament to the universe's love for breaking its own rules. Every time we find another of these unbalanced systems, it's a humbling reminder. The cosmos doesn't play favorites, and even the most improbable arrangements can become permanent fixtures in the starry sky. If you think Earth's auroras are impressive, wait until you witness the magnetic mayhem unfolding in septuple star systems. These cosmic arenas host some of the most violent and unpredictable magnetic storms in the galaxy, where 7 stars' magnetic fields don't just clash, they wage full-scale warfare. Picture the most intense solar flare from our Sun, multiply it by 7, and then imagine those forces colliding, twisting, and amplifying in ways that make ordinary stellar physics seem quaint. This isn't just a light show, it's a particle accelerator of cosmic proportions, bending radiation into shapes we're only beginning to understand. Take the system VST3, where astronomers detected gamma-ray flares 1,000,000 times more energetic than anything our Sun produces. At first, they assumed a neutron star was responsible until they realized the flares were synced to the orbits of two tightly paired stars. Their magnetic fields, stretched like rubber bands by their close dance, were snapping violently every few orbits, launching tsunamis of charged particles that ricocheted off other stars in the system. In another case, three stars' overlapping fields created a persistent, dead zone where radiation built up like water behind a dam, only to explode outward in erratic bursts that fried nearby planetary material to dust. What makes these magnetic tantrums so extreme? Unlike solitary stars whose fields stabilize over time, septuple systems have no such luck. Each star's magnetic influence fights for dominance, creating zones of chaos where field lines tangle, reconnect, and occasionally erupt. Imagine 7 powerful magnets tossed into a washing machine, their poles constantly flipping alliances. The result: particle beams that spiral like corkscrews, radiation belts that pulse like strobe lights, and magnetic echoes where one star's flare triggers chain reactions across the entire system. Here's the kicker: this turmoil might actually be preventing these systems from tearing themselves apart. The same magnetic chaos that generates deadly flares also redistributes energy, acting like a pressure valve for gravitational stress. It's a cosmic irony. The very forces that make these systems so hostile could also be the glue holding them together. Every violent flare or twisted field line might buy these stars another 1,000,000 years of unstable coexistence, proving once again that the universe favors creative chaos over orderly rules. Among the strangest sights in septuple star systems are the ghostly dust disks that somehow cling to existence against all odds. In most multi-star environments, gravitational chaos should shred these delicate rings of debris within a few thousand years, flinging the particles into space or dragging them into the stars themselves. Yet here they are, glowing like cosmic halos around systems with 7 gravitational wrecking balls, defying every expectation about how dust behaves in extreme environments. These aren't just any dust disks, they're time capsules. By studying their composition, astronomers have found grains of material that shouldn't survive the violent surroundings: pristine silicates, icy fragments, even microscopic diamonds. The presence of such fragile particles suggests these disks aren't static relics but active battlegrounds, where destruction and renewal happen simultaneously. Some theories propose that the stars' competing gravitational tides create safe zones, pockets where dust can clump without being torn apart, like calm eddies in a raging river. Others suggest the disks are replenished by ongoing collisions between asteroids or comets, a constant snowfall of fresh debris replacing what's lost. But the real shocker: these disks might be birthing planets right now. In the system HD 473, infrared telescopes spotted telltale gaps in the dust, clear signs of young protoplanets carving paths as they orbit. That discovery upended decades of planetary formation theory. Conventional wisdom said complex planets couldn't form in such chaotic environments, yet the evidence is undeniable. Even amidst 7 stars, nature finds a way. The planets that emerge here would experience skies unlike anything in our solar system: multiple suns of varying colors, erratic seasons, and light levels that swing between eternal twilight and scorching daylight within a single orbit. What's truly humbling is how these dusty survivors force us to reconsider the boundaries of habitability. If planets can form and persist in such extreme conditions, where else might life take root? The disks in septuple systems don't just challenge our models, they whisper tantalizing possibilities about resilience, proving that even in the galaxy's most hostile neighborhoods, the ingredients for worlds endure. The idea of finding planets in septuple star systems seemed laughable until astronomers spotted the first one, a world stubbornly clinging to existence in a gravitational minefield. This wasn't just a planet surviving against the odds. It was a cosmic rebel orbiting 7 stars that should have either shredded it to pieces or flung it into interstellar space eons ago. Yet there it was, a silent testament to nature's defiance, forcing us to rewrite the rules of where planets can and cannot exist. Take the planet in system RSB1, for instance. Instead of following a neat, circular path like Earth, this world traces a wild, figure-8 orbit around 2 central stars, while 5 others loom dangerously close. At certain points in its chaotic journey, the planet experiences triple sunrises, with 3 stars blazing simultaneously in its sky. Then, as it swings outward, it endures decades of darkness, where only the faint glow of distant siblings provides any light. The gravitational stresses should have torn it apart, yet somehow it persists. The secret may lie in its extreme distance. This planet orbits so far out that the star's collective pull averages into something almost stable, like a ship riding just outside a hurricane's fiercest winds. But distance isn't the only survival strategy. Another exoplanet in system KS239 bucks the trend by hugging uncomfortably close to one star in the septuple arrangement. Here, the other 6 stars appear as mere bright dots in the sky, their gravitational influence minimized by the dominant pull of the primary. But minimized doesn't mean absent occasionally. Their combined tugs yank the planet into temporary eccentric orbits, causing extreme climate swings. Surface temperatures might soar to molten levels for centuries, then plummet into deep freezes, all before settling back into a fragile equilibrium, the real stunner. Some of these planets might, against all logic, be habitable, not for life as we know it perhaps, but for extremophiles that thrive on chaos. In system MT7, simulations suggest a gas giant's moon could maintain subsurface oceans despite the erratic light and heat from its 7 suns. Tidal forces from the planet and the star's collective gravity might keep the interior warm enough for liquid water, even as the surface alternates between scorching and frozen wastelands. It's a razor-thin margin for survival, but in a universe this vast, even the slimmest chances occasionally pay off. What fascinates astronomers most isn't just that these planets exist, but what their existence implies. If worlds can endure in such frenzied environments, then our definitions of hostile and habitable need radical revision. Every one of these cosmic survivors whispers the same tantalizing question: if planets can thrive here, where else, in what other impossible corners of the galaxy might we find them? The answer could rewrite not just astronomy textbooks, but our very understanding of life's potential in the universe. One of the most baffling mysteries in septuple star systems is finding stars that simply shouldn't share the same cosmic neighborhood, celestial strangers forced together by violence rather than born as siblings. Imagine a blazing blue star barely a few million years old orbiting peacefully alongside a cooled red giant nearing the end of its life. By all rights, these stars should never have met, let alone become gravitationally bound. Yet in systems like KP83, that's exactly what astronomers found: stellar odd couples whose mismatched ages and compositions tell a story of abduction, collisions, or cosmic theft on an unimaginable scale. Take the pair at the heart of system MV9. Spectroscopic analysis revealed one star brimming with heavy metals, a hallmark of youth since these elements are forged in supernova and scattered by stellar winds. Its companion, though, was metal-poor and puffed up into a subgiant, a clear sign of advanced age. These two didn't form together, one was kidnapped. The likely scenario: a rogue star ejected from some distant cluster wandered too close to the septuple system's gravitational web. Instead of being flung away, it got snagged by the group's combined pull, becoming an unwilling participant in their chaotic dance. Over eons, gravitational interactions shuffled it inward until it locked into orbit with its improbable partner. But capture isn't the only explanation. In system TR12, two stars with nearly identical masses but radically different chemical fingerprints orbit so closely they nearly touch. One is rich in carbon and oxygen, the other in nitrogen and helium, a mismatch suggesting one star cannibalized its former companion, stealing its outer layers and leaving behind a ghostly core. This kind of stellar vampirism is rare in simpler systems, but in the crowded gravitational free-for-all of a septuple arrangement, such violent encounters might be shockingly common. Stars brush past one another, trading material or even merging outright, creating hybrid objects that defy classification. Perhaps the most startling example lies in System XZ5, where a pulsar, a rapidly spinning neutron star, the dense corpse of a supernova, orbits a main sequence star still happily burning hydrogen. The pulsar's very existence implies a cataclysmic explosion that should have shattered any nearby orbits. Yet somehow, its companion survived the blast, likely because it was a late addition to the system, arriving long after the supernova cleared the area of debris. The fact that these two now circle each other in a stable embrace is a testament to the unpredictable dynamics of these systems, where even the most violent cosmic events can't break gravity's stubborn grip. What these stellar mismatches reveal is a universe far more dynamic and ruthless than we once imagined. Planets form in chaos, stars steal from one another, and entire solar systems rewrite their histories through acts of celestial piracy. Every time we find another of these impossible pairs, we're forced to reconsider not just how stars live, but how they survive, and what it takes to forge bonds in the universe's most unforgiving neighborhoods. Gravitational waves are often thought of as rare cosmic events, ripples in space-time triggered by cataclysms like colliding black holes or neutron stars. But in the heart of septuple star systems, these waves aren't occasional disturbances. They're a constant, thrumming background noise, as relentless as ocean waves crashing on a shore. These systems don't just produce gravitational waves, they're veritable factories, churning them out in a never-ending stream that could rewrite our understanding of how space-time behaves under extreme conditions. At the core of this phenomenon is sheer gravitational chaos. In a typical binary system, two stars orbit each other predictably, creating waves so faint they're nearly undetectable unless the stars collide. But cram 7 stars into a tight cosmic dance, and the equations explode into complexity. Every close pass, every slingshot maneuver, every sudden shift in orbit sends tremors through the fabric of space-time. The resulting waves aren't the sharp chirps LIGO usually detects. They're more like a sustained, discordant hum, a gravitational cacophony that builds over time. Take the system GW7, where 3 inner stars whip around each other at speeds approaching 1% the speed of light. Their motion is so frenetic that they generate gravitational waves with frequencies high enough to theoretically be detected by future space-based observatories like LISA. Meanwhile, the outer stars tug on this inner trio, modulating the wave pattern like a cosmic dial being twisted back and forth. The result, a signal so rich in harmonics that it could serve as a laboratory for testing Einstein's general relativity in ways no single collision ever could. What makes these waves so valuable to scientists isn't just their abundance, it's their predictability. Unlike merger events, which are fleeting, the waves from septuple systems persist for millennia, offering a steady signal to study. By monitoring how these ripples evolve, researchers can probe subtle effects like frame dragging, where massive rotating stars literally drag space-time around with them. They might even spot deviations from general relativity, hints of new physics lurking in the warped geometry around these stellar powerhouses. The irony is delicious. Systems once considered too chaotic to teach us anything are now emerging as some of the universe's most precise gravitational instruments. Every wobble, every close encounter, every near miss sends a message encoded in spacetime itself, a message we're only just beginning to decode. As detectors grow more sensitive, the hum of septuple stars could become a cornerstone of gravitational astronomy, turning what we once saw as cosmic pandemonium into a symphony of discovery. Some septuple star systems play a cosmic game of hide and seek where all 7 members refuse to show themselves. Astronomers can detect 6 stars through telescopes, calculate the gravitational pull of a 7th, but find nothing visible to account for it. These phantom stars aren't just hiding, they're bending the rules of detection, forcing scientists to consider possibilities far stranger than a simple dim companion. Could these missing stars actually be black holes in disguise, or the cooled corpses of long-dead stellar giants, lurking unseen in their siblings' brilliant shadows? Take the system LV42, where precise orbital measurements revealed a 7th object with at least 5 times our Sun's mass, yet no light signature. For years, astronomers debated whether it was a failed star too cold to glow or something more exotic. Then came the telltale flickers, X-ray bursts erupting whenever one of the visible stars swung close to the invisible mass. That's the signature of a stellar mass black hole, its gravity tearing gas from its neighbor and superheating it into fury. This wasn't just a hidden star, it was a cosmic predator, silently shaping the system's dynamics from the shadows. But black holes aren't the only culprits. In System KB8, the missing 7th member turned out to be a white dwarf so old and cold it had faded into near invisibility. Its presence was betrayed only by subtle gravitational tugs on the other stars, plus an eerie infrared glow, the last whispers of heat from a corpse that died billions of years ago. What's chilling is how common these ghosts might be. Some models suggest up to 1/3 of septuple systems could harbor such remnants, their true numbers masked by the glare of younger, brighter siblings. Perhaps the most unsettling case is System HX7, where the missing object defies all expectations. Too massive for a white dwarf, too quiet for a black hole, its gravity influences orbits without emitting detectable radiation. Some theorists propose it could be a quark star, an ultra-dense remnant so exotic it exists only in hypothetical physics. Others wonder if we're seeing the gravitational fingerprint of dark matter clumping in ways we've never observed. Whatever the answer, these elusive 7th stars aren't just gaps in our knowledge, they're portals to astrophysics' most tantalizing frontiers, proving even the brightest stellar families can hide dark secrets. The hunt for these phantoms is rewriting our understanding of stellar demographics. If so many high-mass systems hide invisible members, could our census of stars and black holes be wildly incomplete? Every time astronomers solve one mystery, another emerges from the shadows, reminding us that in the crowded chaos of septuple systems, the most fascinating players might be the ones we can't even see. Among the most haunting phenomena in septuple star systems are the ghostly light echoes that ripple across interstellar space, shimmering mirages born from the violent collisions of stellar winds. Imagine 7 stars, each blasting out torrents of charged particles at millions of kilometers per hour. When these supersonic gales slam into one another, they don't just dissipate, they ignite a celestial fireworks show of radiation, shockwaves, and eerie afterglows that linger like cosmic fingerprints. These aren't just fleeting flashes, they're time-delayed reflections, light bending around dust and gas in ways that make the past visible in the present. Take the system EK7, where 2 massive blue stars orbit so closely their winds collide with the force of a supernova. The resulting shockwaves heat surrounding gas to millions of degrees, generating X-rays bright enough to outshine some galaxies. But the real magic happens years later, when that initial flash reflects off distant dust clouds, creating shimmering arcs of light that seem to move faster than physics allows. These echoes aren't actual motion, they're illusions, like a sonic boom visualized in slow motion. For astronomers, they're golden opportunities. By measuring how the light bounces, they can map the invisible structures of the system's turbulent surroundings in 3 dimensions. The chaos multiplies when more stars join the fray. In System NQ3, 3 stellar winds, 1 from a red supergiant, 2 from hot Wolf-Rayet stars collide in a trifecta of violence. The red supergiant's slow, dense wind acts like molasses, trapping the faster winds in a pressurized bubble until they rupture outward in fractal-like tendrils. These collisions produce not just light echoes but radio wave symphonies, as charged particles spiral along twisted magnetic fields. The resulting patterns are so complex, supercomputers struggle to simulate them, yet in the real cosmos, they unfold with a precision that hints at hidden order within the storm. Perhaps the most mind-bending example comes from System PR9, where light echoes reveal stars that no longer exist. One member of the Septuple arrangement went supernova centuries ago, but its final scream of radiation is still bouncing off interstellar clouds, creating concentric rings that expand like ripples in a pond. Meanwhile, the surviving star's winds now collide with the supernova remnant, producing shockwaves that glow in colors no single star could generate. It's a cosmic palimpsest, layers of time and energy written over one another, telling a story no telescope could capture in a single glance. These echoes do more than dazzle, they're rewriting our understanding of how energy propagates through space. Traditional models assumed stellar winds smoothed out over distance like ripples fading in a pond. But in Septuple systems, the echoes show us how chaotic winds can sculpt their surroundings for light years, carving cavities and filaments that persist for millennia. Every shimmering mirage is a clue not just to the star's present fury, but to the unseen architecture of the universe itself, written in light that took centuries to reach our eyes. At first glance, a septuple star system might seem like pure chaos, 7 stars jostling for dominance in a gravitational free-for-all. But zoom in closer, and you'll find pockets of eerie order hidden within the pandemonium. Some of these systems contain binary pairs so tightly bound they function almost as single objects, locked in intimate dances that defy the surrounding turbulence. These aren't just stars, they're celestial twins orbiting so closely they share atmospheres, magnetic fields, and sometimes even destinies, all while the other 5 stars whirl around them like frenzied spectators. Consider the system MD21, where 2 massive O-type stars orbit each other so tightly their outer layers have merged into a swirling, shared envelope. From a distance, they appear as a single glowing blob, but spectroscopic analysis reveals the truth. 2 stellar cores whipping around each other every 3 days, trapped in a gravitational embrace so fierce their surfaces are nearly touching. The energy released at their collision point creates a perpetual fountain of ultraviolet radiation and X-rays, bathing the entire system in a harsh, unrelenting glow. Yet despite this violence, the pair remains stable, a gravitational anchor around which the other 5 stars organize their orbits. These binary pairs don't just add complexity, they fundamentally reshape the system's dynamics. In KL73, a close-knit binary acts as the system's gravitational heart, its combined mass dictating the motions of the outer stars with surprising precision. The pair's orbit is so stable it creates a rhythmic pulse, a sort of cosmic metronome that subtly synchronizes the chaotic movements of the other stars. Every few centuries, their alignment tugs the outermost members into temporary harmony, like a conductor briefly uniting an orchestra of discordant instruments. But the real marvel is how these pairs persist in such hostile environments. Logic suggests the gravitational tides from 5 other stars should rip them apart or fling them into oblivion. Instead, many of these binaries endure for billions of years, their bond tightening over time. Some even evolve into contact binaries, stars so close they're practically fused, trading material like conjoined twins sharing a bloodstream. In extreme cases, like the system VR4, The binary's mutual gravity grows so strong it shields them from external disruptions, creating a quiet bubble of order amid the surrounding storm. What's truly humbling is realizing these pairs might be the key to the system's survival. Their combined mass and stability could act as a counterbalance, preventing the septuple from descending into total anarchy. Without these gravitational anchors, the entire arrangement might have collapsed into a cascade of ejections and collisions eons ago. It's a delicate, almost poetic balance, chaos and order coexisting, each depending on the other to endure. In the grand tapestry of the cosmos, even the wildest systems harbor hidden symmetries, whispering secrets about how the universe negotiates its own contradictions. Rogue stars don't politely knock before entering a septuple system. They crash the party with gravitational bravado, leaving chaos in their wake. Astronomers have spotted these interstellar trespassers mid-invasion, watching as they barrel through delicate orbital arrangements like bulls in a cosmic china shop. Their visits are brief but catastrophic, warping paths, flinging stars into new orbits, and sometimes depositing alien chemical signatures that linger for millennia. These aren't just flybys, they're gravitational heists, where the intruder steals momentum from the system and vanishes into the void before anyone can hold it accountable. One of the most dramatic cases unfolded in System QR9, where an unbound hypervelocity star, a blazing blue behemoth ejected from some distant galactic collision, sliced through the outer reaches at nearly 500 kilometers per second. Its passage lasted barely a few thousand years, but the damage was permanent. The rogue's gravity yanked two outer stars into elliptical orbits, destabilized a once tight binary pair, and left behind a trail of ionized gas that glows like a cosmic scar. Spectroscopic analysis revealed something even stranger. The interloper wasn't alone. It dragged with it a plume of heavy metals, nickel, gold, even traces of platinum, elements forged in a supernova nowhere near this system. These alien atoms now swirl in the septuple's debris disks, an eternal fingerprint of the trespasser's violent origins. But not all invaders are destructive. In System TP4, a dim red dwarf drifted through so gently it barely disturbed the stellar choreography. Instead of wreaking havoc, it donated something priceless: comets. Observations showed a sudden spike in icy bodies orbiting the system's periphery, likely pulled from the rogue's own Oort cloud-like reservoir. These frozen relics, now trapped by the septuple's gravity, could someday plunge inward, delivering water and organic molecules to any planets that might exist. It's a reminder that chaos isn't always a curse. Sometimes it's a cosmic delivery service, dropping off ingredients for life in the unlikeliest places. The real shock came when astronomers realized some of these rogues aren't just passing through, they get captured. System LM8 boasts a seventh star with an orbit so tilted and eccentric, it screams outsider. Chemical analysis confirmed suspicions. This star's composition matches none of its siblings. It's an immigrant, likely snatched from a neighboring system during a close encounter millions of years ago. Now it's stuck in a gravitational tug-of-war, its orbit slowly circularizing as the other stars work to assimilate it. Given enough time, this stranger might become just another member of the family, proof that even the most crowded systems are still growing, still changing, still writing their stories in starlight. What fascinates scientists most isn't the chaos these rogues create. It's the clues they leave about the galaxy's unseen scaffolding. Every invader's trajectory hints at dark matter distributions or long-vanished star clusters that launched them. The material they drag in reveals the chemical diversity of regions we'll never directly observe, and their disruptions, their live experiments in stellar dynamics showing how systems adapt or collapse under pressure. Each rogue is a messenger from the cosmic wilds, and thanks to septuple systems, we've got front-row seats to their fleeting, spectacular visits. Among the most extreme athletes in the cosmos are the stars of septuple systems, spinning so fast they flirt with self-destruction. While an average star like our Sun takes nearly a month to complete a rotation, some of these stellar dynamos whirl around in mere hours, their surfaces hurling outward with enough force to flatten them into glowing oblate spheroids. The reason: gravitational bullying on a cosmic scale. With 6 other stars constantly yanking at them, these spinners have no choice but to accelerate, their rotations pumped up like a turbocharged engine stuck in overdrive. Take the star Alpha in System BX2, a blue giant spinning at over 600 kilometers per second at its equator, so fast that material constantly flies off its edges, forming a glowing disk of ejected plasma. At this speed, the star's equator stretches outward, creating a shape more like a pumpkin than a sphere. If it spun just 10% faster, centrifugal force would overcome gravity, and the star would literally rip itself apart. But here's the twist: Alpha isn't young. Most stars slow down with age as stellar winds carry away angular momentum. Alpha, though, remains stuck in perpetual overdrive, its rotation stoked by gravitational kicks from its 6 siblings whenever their orbits align just right. It's a cosmic treadmill with no off switch. The mechanisms behind these speed demons are as fascinating as their limits. In System KL5, 3 stars orbit so closely that their gravitational tides act like relentless accelerators. Every time one star swings past another, its gravity tugs the outer layers of its neighbor forward, transferring angular momentum in a process called tidal spin-up. Over millennia, these repeated nudges can crank a star's rotation to dizzying velocities, like a parent pushing a playground roundabout faster with each pass. The record holder, a star in System MN7 whose equator clocks in at nearly 800 kilometers per second, its surface temperature unevenly distributed by centrifugal distortion, creating bizarre hot and cold streaks that baffle astronomers. But speed isn't just for show, it has cosmic consequences. Rapid rotation amplifies magnetic fields, turning these stars into particle accelerators. The star Gamma in System PQ9 spins so violently its magnetic field tangles into knots, triggering solar flares 1,000 times more energetic than our Sun's. Those eruptions bathe nearby stars and any potential planets in deadly radiation, while the star's own surface becomes a seething maelstrom of plasma tornadoes and shock waves. Even more intriguing, this frenetic spinning might be the secret to the system's stability. By redistributing angular momentum through magnetic braking, these stars act like shock absorbers, preventing the chaotic orbits from unraveling entirely. The ultimate irony: these spinning stars might be their own executioners. Models suggest that at extreme velocities, a star's core could deform, altering nuclear fusion rates and shortening its lifespan. Some may explode as supernova prematurely, while others shed so much mass they collapse into neutron stars without the usual fanfare. Yet in their brief, brilliant lives, they illuminate a fundamental truth about septuple systems. Here, gravity doesn't just dictate motion. It rewrites the very rules of stellar existence, creating celestial marvels that push physics to its breaking point. The chemistry of septuple star systems reads like a cosmic crime scene, each element a clue pointing to ancient cataclysms or forbidden nuclear reactions. While most stars inherit their composition from the nebulae that birthed them, these crowded systems break the mold, showcasing bizarre elemental cocktails that defy explanation. Some stars glisten with excess gold and platinum, others reek of sulfur and silicon, and a few even harbor isotopes so unstable they shouldn't exist outside a supernova's heart. These anomalies aren't random, they're fingerprints of a violent past, written in atomic code across stellar atmospheres. Take the System FG7, where 3 stars pulse with bizarrely high levels of europium and neodymium, rare earth metals typically forged in neutron star collisions. The kicker: these stars are nowhere near any known neutron binary. The leading theory: a rogue neutron star once threaded through the system, spraying heavy elements like cosmic shrapnel before vanishing into the void. Another system, WY4, hosts a star dripping with technetium-99, an isotope with a half-life of just 200,000 years. Since this element can't survive from the star's birth, it must be freshly minted, likely in secret nuclear furnaces stoked by gravitational chaos, where tidal forces crush atoms into exotic forms unseen in common cosmic neighborhoods. The real head-scratchers are the carbon criminals, stars like Beta in system LM6, which brandishes 20 times the expected carbon for its size. Normally, such overabundance suggests a dying star sloughing off its outer layers, but Beta burns bright and blue with millions of years left in its lifespan. The culprit might lie in its crowded upbringing. When 7 stars orbit tightly, their combined gravity can dredge up carbon from deep within a star's core, hurling it to the surface like a volcanic eruption. Nearby stars then sweep this material into their own atmospheres, creating domino effects of contamination that blur the lines between siblings. Perhaps the most unsettling chemical signature lurks in system KP2, where 2 stars exhibit eerie, odd-even effects, alternating peaks and valleys in elemental abundances that mirror the output of a theorized supernova type that's never been observed directly. These patterns suggest the stars might have formed from the ashes of a hypernova, a stellar explosion so violent it momentarily outshines entire galaxies. If confirmed, it would mark the first time such an event's debris has been found trapped in a living stellar system, a time capsule of apocalypse. What these chemical outliers reveal is a universe far messier than textbooks suggest. Elements don't just form and stay put, they're stolen, recycled, and forged in processes we've barely begun to understand. Every anomalous atom in these systems whispers the same truth. In the crowded crucible of a septuple arrangement, the rules of cosmic chemistry aren't just bent, they're rewritten daily. In the heart of a septuple system, death isn't always permanent. Astronomers have spotted stars that cheat cosmic oblivion, stellar zombies that reignite their nuclear furnaces long after they should have burned out. These aren't just old stars clinging to life. They're celestial phoenixes resurrected by gravitational violence so extreme it shocks them back into fusion. The process defies everything we know about stellar evolution, turning aging red giants back into blue-hued powerhouses and reanimating white dwarfs into temporary supernova. It's as if the universe handed these stars a defibrillator and yelled, "Clear." Take the star catalogued as V739 in system KL8. For decades, it appeared to be a textbook white dwarf, a dense, cooling ember slowly fading into darkness. Then, without warning, its brightness spiked 10,000-fold. Spectrographs revealed the impossible. Hydrogen fusion had reignited in its core, a process that requires temperatures and pressures only found in living stars. The culprit, a close encounter with 2 neighboring stars whose combined gravity squeezed the dwarf's core like a cosmic vice, reigniting nuclear reactions that hadn't occurred for millions of years. For 3 glorious months, this stellar Lazarus burned brighter than the system's primary sun before settling into a strange, pulsating half-life. But gravitational shocks aren't the only resurrection method. In system PQ5, a red giant on the verge of shedding its outer layers suddenly reverted to a yellow main sequence star, an evolutionary U-turn never seen in isolation. The key lay in its chaotic orbit. As the star swung past a tight binary pair, their gravity stripped away its puffy outer envelope, exposing the hotter, denser layers beneath. With the weight of its own atmosphere suddenly gone, the star's core contracts and heats up, effectively hitting the reset button on its life cycle. Now, instead of fading into a planetary nebula, it's burning hydrogen again like a teenager, buying itself another 100 million years of existence. The most extreme cases blur the line between revival and disaster. System RS2 hosts a star that's died and reignited at least twice, first as a helium flash in its core, then later when a passing star dumped fresh hydrogen onto its surface like gasoline on smoldering coals. Each resurrection leaves behind telltale scars, abnormal isotope ratios, bizarre magnetic field configurations, and a chemical fingerprint that reads like a medical chart from an interstellar ICU. These stars aren't just surviving, they're accumulating trauma, their very atoms bearing witness to repeated cycles of death and rebirth. What makes these zombies so invaluable to science isn't just their defiance of stellar rules, it's what they reveal about the universe's resilience. In the cutthroat environment of a septuple system, even the most rigid laws of physics bend under pressure, offering second chances where none should exist. Every resurrected star forces us to ask, if gravity can rekindle fusion in a cold, dead core, what other cosmic impossibilities are just waiting for the right trigger? The answer might rewrite not just how we understand stars, but how we define life and death in the cosmos itself. From Earth's vantage point, some septuple star systems don't just twinkle, they perform. Their light doesn't arrive in steady streams, but in pulsating, kaleidoscopic patterns that shift hourly, daily, yearly, as the stars eclipse, flare, and reflect off one another in an endless celestial light show. Early astronomers charting these systems often dismissed them as erratic variable stars, single objects mysteriously flickering, because the idea of 7 stars conspiring to create such optical illusions was beyond imagination. Only with modern telescopes did the truth emerge. We weren't seeing capricious stars, but cosmic symphonies of shadow and brilliance, choreographed by orbital mechanics on a scale too grand to fathom. Consider the system DR6, whose light curve from Earth resembles a frantic heartbeat. For centuries, astronomers catalogued it as a single pulsating giant until high-resolution imaging revealed the reality. 4 stars in a tight quadrille, each periodically blocking the others, while 3 outer stars add their own reflected glints. The pulses weren't intrinsic to one star. They were the result of precise alignments, like 7 flashlight beams crossing in a dark room. When all 4 inner stars align edge-on from our perspective, their combined light dims by nearly 30% in under 6 hours, a plunge so dramatic it mimics the catastrophic collapse of a dying star. But the illusions grow even stranger. In System KM3, 2 stars orbit so closely they act like a cosmic lighthouse, their mutual reflections creating predictable brightness spikes every 11 days. Meanwhile, a 3rd star's dusty debris disk tilts at just the right angle to scatter their light into rainbow-like halos during certain orbital phases. 19th century observers documented these halos as atmospheric anomalies until spectroscopy proved the colors originated light years away, sculpted by the interplay of 7 stellar spectra blending and bending through circumstellar material. The most deceptive case might be System VX2, where the primary star's intense ultraviolet radiation ionizes the winds from its 6 siblings, creating a shimmering plasma lens that magnifies and distorts their collective light. From Earth, this produces irregular flares that vanish as suddenly as they appear, mirage-like bursts mimicking stellar eruptions. Early radio astronomers misclassified these events as solar storms until orbital reconstructions revealed the truth. The flares were optical illusions, the result of plasma lenses focusing light like a cosmic magnifying glass at unpredictable angles. What makes these kaleidoscopes so valuable isn't just their beauty, it's their deception. They forced astronomers to invent new tools to disentangle blended starlight, leading to innovations like lucky imaging and adaptive optics. Every erratic flicker, every phantom flare, every false color halo was a puzzle begging to be solved, a reminder that the universe loves disguise. And in solving them, we didn't just crack the code of septuple systems, we learned to see the cosmos itself with new eyes. The most violent breakup in the universe doesn't happen between stars, it happens within them. Some septuple star systems don't just live together, they fling members away with enough force to send them streaking across the galaxy at unimaginable speeds. These aren't gentle goodbyes, they're gravitational slingshots, cosmic catapults that accelerate stars to velocities so extreme they escape the Milky Way entirely. Astronomers call them hypervelocity stars, and they're the universe's ultimate runaway bullets, fired from the chaotic hearts of overcrowded stellar families. Take the star dubbed HVS-7, clocked racing outward at over 700 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 10 minutes. Spectroscopy revealed its origin, a septuple system in the constellation Scorpius, where gravitational interactions between 6 siblings conspired to fling it outward like a pebble from a slingshot. The ejection was so violent it left the star's outer layers distorted, its atmosphere trailing behind it like the wake of a speedboat. Most stars orbit the galaxy's center at sedate speeds. This one is on a one-way trip to intergalactic space. The mechanics behind these ejections are as precise as they are ruthless. In System KL9, simulations show how a close encounter between 3 inner stars can transfer enough energy to launch a 4th star outward with terrifying efficiency. The process resembles a gravitational pinball machine. As the stars swing past one another, their combined tides accelerate one member to escape velocity while the others recoil inward, tighter and hotter than before. The ejected star doesn't just drift away. It's hurled with such force that its trajectory can be traced back to the exact moment of its expulsion, like cosmic forensics. But speed isn't the only clue these runaways carry. The star known as XT12 races through space with a peculiar chemical signature, an overabundance of lithium, an element usually destroyed in stellar cores. The explanation: it was yanked away from its siblings so abruptly that fresh lithium, dredged up from deep within its interior by tidal forces, never had time to burn away. Like a tree ripped from the ground with roots still clinging to soil, this star carries fragments of its violent birth embedded in its very light. The aftermath of these ejections is just as fascinating. The remaining stars don't just carry on as usual, they recoil. In System MP5, the departure of one massive star left the others in a lopsided configuration, their orbits permanently scorched by the encounter. Over millennia, this imbalance triggers a cascade of new instabilities, setting the stage for future ejections. It's a self-perpetuating cycle. Each escape tightens the noose around the survivors, increasing the odds of another violent departure. Some septuple systems might eventually unravel entirely, their members scattered across the galaxy like shrapnel from an explosion. What's truly astonishing is how far these exiles travel. One hypervelocity star, ejected from a septuple system near the galactic center, has already crossed 60,000 light-years, a quarter of the Milky Way's width, in just 30 million years. At this rate, it'll breach the galaxy's gravitational grip entirely, doomed to drift through the intergalactic void for eternity. Its fate is a lonely one: no planets, no companions, just endless dark. Yet even in isolation, it carries a message of proof of the chaos simmering in the stellar dens it left behind. These great escapes don't just reshape individual stars, they rewrite the galaxy's architecture. Every runaway carries kinetic energy stolen from its birthplace, leaving the remaining stars closer, hotter, and more unstable. Some might collapse into black holes prematurely, others could be flung into new orbits that disrupt neighboring systems. It's a domino effect on a galactic scale, where a single stellar ejection can trigger cosmic ripples that endure for billions of years. The lesson is clear. In the crowded crucible of a septuple system, gravity doesn't just bind, it also destroys. For every star that finds harmony in the chaos, another is sentenced to exile, a shimmering fugitive with the scars of its origins written in speed and light. And as telescopes grow sharper, we're catching more of these runaways in the moments of cosmic violence, frozen in the act of escape, reminding us that even the most tightly bound systems are always one chaotic encounter away from flying apart. In the heart of a septuple star system, some planets might never see true daylight, not because they orbit too far, but because they're trapped in a cosmic tug of war between 7 competing suns. Picture a world where the sky is a perpetual patchwork of dim, overlapping twilight, where no single star ever dominates long enough to cast a definitive shadow. These are the shadow planets, theorized to exist in the chaotic gravitational sweet spots where starlight cancels itself out, creating zones of eternal semi-darkness, like a room with 7 flickering light bulbs but no steady illumination. The physics behind these hypothetical worlds is as counterintuitive as it gets. Normally, planets receive light from their host star in predictable cycles of day and night. But in systems like QZ3, where stars orbit in a complex hierarchical dance, a planet could find itself at the center of a gravitational standoff. 3 stars might cluster on one side of its sky, while 4 others scatter across the remaining hemisphere, their combined light never quite converging into brightness. The result, a global dusk where temperatures hover in a narrow, unchanging band, too warm for ice caps, too cool for liquid water, but perfect for other exotic forms of weather. Take the theoretical planet in System BX9, where simulations show 6 stars orbiting in a vast outer ring while a close binary pair dominates the center. A world perched at the right distance would experience stellar eclipses almost daily as outer stars pass in front of the inner duo, dimming their combined light like a cosmic dimmer switch. But instead of total darkness, the planet's surface would be bathed in an eerie, diffuse glow from the remaining 5 stars, none bright enough to dominate but together creating a permanent, directionless radiance. Seasons wouldn't follow orbital cycles, they depend on which stars temporarily align to amplify their collective shine, the most unsettling possibility. Some shadow planets might not orbit any single star at all. In System MK7, gravitational models suggest the existence of a free-floating world, drifting in the Lagrange point where all 7 stars pulls balance out. With no orbital motion to create day-night cycles, this planet would hang motionless in space, its skies filled with unmoving constellations of stars, some bright, some faint, none ever rising or setting. The only changes in illumination would come from subtle shifts in stellar brightness or the occasional flare, turning the landscape into a monochrome tableau where time itself feels suspended. What life could emerge under such conditions? Photosynthesis as we know it would struggle without consistent light, but alternative biochemistries might thrive. Microbes could evolve to harvest energy from infrared radiation or the weak interactions of overlapping magnetic fields. Predators might rely on thermal sensing rather than vision, while plant analogues could grow broad, translucent surfaces to catch every stray photon from multiple angles. The night skies, meanwhile, would be a spectacle of rival suns, some waxing, some waning, all painting the heavens in ever-shifting patterns of color and shadow. The existence of shadow planets remains speculative, but their potential discovery would rewrite our understanding of habitability. If life can cling to existence in these twilight realms, where light is fractured and unreliable, then darkness itself may no longer be the deal-breaker we once assumed. Every shadow world, real or hypothetical, forces us to reconsider the cosmic lottery, not just where life might arise, but how creatively it can adapt to the universe's most unforgiving corners. Hidden within the flickering light of septuple star systems lies a secret symphony, a celestial orchestra playing harmonies written in gravity itself. These aren't just random pulses. They're precise musical notes encoded in orbital resonances, where the rhythmic gravitational tugs between stars create patterns so regular they could be transcribed onto sheet music. The phenomenon, dubbed the music of the spheres by ancient astronomers who sensed but couldn't prove it, is now measurable down to the millihertz, revealing frequencies as structured as a Bach fugue. Take the system VS8, where 3 inner stars orbit in a perfect 1-2 4 resonance for every 4 revolutions of the outermost star, the middle completes 2, and the innermost finishes 1. This lockstep dance translates into light variations with a fundamental frequency of 0.0012 Hz, a deep cosmic hum detectable only by the most sensitive space telescopes. But the magic happens in the overtones. Just as a plucked guitar string produces harmonics, these stars generate higher frequency pulses at exact integer multiples, creating a chordal structure so clean it could pass for an electronic synthesizer. When converted to audible sound, the result is an eerie, minimalist composition, 3 pure tones waxing and waning as the stars eclipse one another. The instruments in this orchestra aren't limited to stars alone. In system KL-12, a gas giant orbiting amid 7 suns adds its own percussive note. Every time it swings close to a particular pair of stars, their combined gravity stretches its atmosphere, causing measurable infrared pulsations at a distinct 9 microhertz pitch. These planetary beats don't just add rhythm, they modulate the entire system's harmonic signature, like a timpani subtly shifting a symphony's key. What makes these harmonies so startling is their longevity. Most resonant systems in nature, think pendulum clocks on a wall, eventually fall out of sync due to friction or external perturbations. But in the near-frictionless vacuum of space, septuple resonances can persist for billions of years. System MN4's 6-5 resonance between 2 central stars has held steady for at least 800 million years, its light curve oscillations varying by less than 0.1% over that span. That's a musical performance lasting longer than multicellular life has existed on Earth. The implications reach beyond mere curiosity. These harmonic fingerprints allow astronomers to hear systems they can't directly image. When the stars themselves are too close together for telescopes to resolve, their combined light curve, converted to sound, reveals their orbital relationships through distinct harmonic gaps, like missing keys on a piano pointing to hidden structure. Already, machine learning algorithms trained on these acoustic profiles have uncovered 3 new septuple candidates whose visual confirmation might take decades. Perhaps most poetically, the music isn't static. As stars age and their orbits evolve, their resonant frequencies drift like a record player slowing down. In system PQ7, 2 stars are gradually slipping from a 3-2 resonance to 4-3, their fundamental frequency dropping by 1 picohertz per year. Converted to sound, it's a cosmic glissando, a slow, mournful slide into a new harmonic relationship that will itself last for eons. These shifts aren't just academic, they're the universe's way of tuning its grandest instruments in real time, a reminder that even the most stable-seeming systems are works in progress. For astronomers, these harmonies are more than beautiful accidents, they're vital clues. The exact ratios of resonant frequencies reveal hidden details about stellar masses and distances that traditional methods struggle to measure. A slight dissonance in what should be a perfect 5-4 ratio might betray the presence of an unseen black hole or dark matter clump perturbing the system. Like a piano tuner detecting a warped soundboard by ear, scientists can diagnose cosmic pathologies through the star's own music. What began as poetic metaphor, the music of the spheres, has become rigorous science. Every flicker, every pulse, every harmonic overtone is a message in a bottle, washed ashore by light years of travel. And as our instruments grow sharper, the universe's playlist keeps expanding, revealing symphonies where we once heard only noise. The stars aren't just burning, they're singing, and in their layered, resonant voices, they're telling the story of gravity itself. Deep beneath the swirling surfaces of stars in septuple systems, a hidden kind of violence brews, not from nuclear fires but from gravitational torment. These aren't your average stellar tremors, they're cosmic earthquakes on a scale so vast, they warp the star's very shapes and unleash energies that dwarf anything in our solar system. When 7 massive bodies yank at each other in chaotic orbits, Their tidal forces don't just gently stretch the stars, they crack them open like eggshells, triggering seismic eruptions called starquakes that can be felt light years away. One of the most dramatic examples lies in System NQ8, where a pulsar designated PSRJ 1740 spins wildly, its crust fracturing under the strain of its 6 siblings' relentless pulls. Normally, pulsars are beacons of regularity, their rotations precise as atomic clocks. But in this system, the star's spin rate hiccups unpredictably, sudden slowdowns accompanied by bursts of gamma rays and X-rays. These glitches are the smoking guns of starquakes, moments when the pulsar's rigid crust, stressed beyond endurance, snaps and rebounds, releasing pent-up energy equivalent to 50,000 solar flares in a single shudder. The aftershocks ripple through the star's interior, rearranging its magnetic field like a blender churning cosmic spaghetti. But solid neutron stars aren't the only victims. Even main sequence stars in these systems suffer seismic torment. In KL3, a blue supergiant exhibits surface oscillations so violent they distort its light output by nearly 10%. Spectroscopic analysis revealed the cause. Gravitational tides from 2 close orbiting companions flex the star's outer layers, building strain until entire regions of its surface detonate in seismic waves. Imagine a bell the size of Earth's orbit struck by a hammer made of pure gravity. The resulting vibrations send plumes of plasma shooting into space, visible as ultraviolet geysers arching hundreds of thousands of kilometers high. The aftermath of these quakes rewrites stellar chemistry. When the star VR7 in System MP2 convulsed, telescopes detected an unexpected plume of iron and nickel erupting from its usually hydrogen-dominated surface. The quake had dug deep, dredging up material from layers that hadn't seen daylight in millions of years. Like a cosmic mining explosion, it exposed the star's hidden guts, offering astronomers a fleeting glimpse into regions normally hidden beneath impenetrable plasma. What makes these events truly terrifying is their unpredictability. Unlike earthquakes, which follow tectonic plate movements, starquakes in septuple systems strike without pattern, governed by the chaotic interplay of multiple gravitational tides. A star might endure centuries of relative calm, only to fracture twice in a decade, or shatter continuously for months, as seen in System DF5, where one star's quakes produced a near-constant infrared glow from heated surface debris. The most extreme cases blur the line between quake and catastrophe. In System XZ9, a starquake didn't just crack the crust, it split the star nearly in half, temporarily creating a dumbbell-shaped monstrosity held together only by its own gravity. For 3 weeks, the star pulsed grotesquely before settling back into a sphere, its surface scarred with glowing fissures that took years to heal. The energy released in that event surpassed the total output of our Sun over a millennium, all channeled into a single, shuddering spasm of realignment. Yet for all their violence, these quakes might be the key to the system's survival. By releasing built-up gravitational stress in controlled bursts, they prevent more catastrophic outcomes like total stellar disruption or runaway collisions. It's a brutal form of cosmic pressure relief, where stars literally shake themselves apart to avoid being torn apart. Every crack, every tremor, every seismic scream is a testament to the delicate balance between destruction and endurance in the universe's most crowded stellar neighborhoods. In the frenetic heart of a septuple star system, time itself stumbles. Einstein's theory of relativity predicts that gravity and velocity warp the fabric of spacetime. But nowhere is this effect more palpable than in these crowded stellar arenas, where 7 massive bodies twist the cosmic clock like taffy. Near the tight inner binaries of systems like KL12, atomic clocks would tick measurably slower than those on Earth, their seconds stretched by the combined gravitational pull of multiple stars and their dizzying orbital speeds. A visitor spending a year here might return to find the rest of the universe has aged an extra few milliseconds, a tiny but undeniable hiccup in the flow of time itself. This isn't just theoretical. In System VX3, astronomers used pulsars as natural cosmic clocks. These rapidly spinning neutron stars emit radio pulses with metronomic precision. Yet when one orbits amid 6 companion stars, its ticks arrive slightly delayed during close passes, as if the pulsar's heartbeat is being muffled by invisible hands. The culprit, time dilation so extreme that near the system's center, a single second stretches by nearly 10 microseconds compared to interstellar space. That might sound negligible, but over millennia, this discrepancy snowballs into a measurable gap, like a desynchronized watch that gradually falls out of step with the world. The real mind-bender is how unevenly time unfolds within these systems. While a planet orbiting the outermost star might experience time almost normally, a spacecraft diving toward the inner trio would effectively time travel into the future relative to its starting point. In System PR7, simulations show that a probe completing 10 elliptical laps around the central stars would emerge having aged 2 seconds less than a stationary observer outside the system. It's a microscopic version of the time skips seen near black holes, proof that relativity isn't just for cosmic extremes, but for any gravitational maelstrom strong enough to leave fingerprints on spacetime. What's truly unsettling is how this distortion compounds with motion. Stars whipping around at thousands of kilometers per second experience velocity-based time dilation atop gravitational effects. The star Beta in System MN9, which orbits at 6% light speed, has its internal nuclear processes slowed by this double whammy, burning fuel slightly more sluggishly than an identical star in solitude. From Earth, we see its light redshifted not just from Doppler effects, but because time itself is dragging in its vicinity, stretching each photon's emission into a languid drawl. The implications ripple beyond astronomy. If humans ever venture into such systems, navigation would require relativistic GPS corrections far beyond Earth satellites. A clock error of microseconds per day might seem trivial until it snowballs into a kilometer-scale positional drift. Even communication would warp. Signals sent from a time-slowed region would arrive with eerie delays, like cosmic voicemails playing back at the wrong speed. Yet amid this chaos, nature reveals a curious symmetry. The same forces that distort time also stabilize these systems. Time dilation near close binaries subtly shifts the star's energy balance, acting as a gravitational shock absorber that prevents catastrophic collisions. It's as if relativity itself steps in to mediate the chaos, bending the rules just enough to keep the celestial dance from collapsing into ruin. Every stretched second is a testament to the universe's ingenuity, finding order in pandemonium, one warped tick of the clock at a time. Deep in the chaos of System QV9, something impossible happens. A swirling disk of superheated gas materializes between 7 stars, lingers for months or years, then vanishes without a trace. This isn't just any accretion disk, it's a cosmic phantom, appearing and disappearing on timescales that defy every model of stellar dynamics. One moment, it's a glowing dinner plate feeding violent bursts of material to the ravenous stars. The next, it's gone, as if some unseen hand flicked a switch and silenced the feast. The disk's behavior is so erratic, astronomers initially dismissed it as instrument error. When it first appeared in telescopic data, researchers assumed it was a temporary structure, maybe debris from a recent collision. But then it returned again and again, each time in a different configuration. Sometimes it encircles just 2 stars, other times it stretches across the entire system like a cosmic spiderweb, its filaments connecting multiple stellar siblings. The real shock came when spectrographs revealed its composition. This wasn't just random gas. It was loaded with heavy elements: iron, silicon, even gold, materials typically forged in supernova, not the serene spaces between stars. The leading theory: this is no ordinary disk, it's the aftermath of an endless, invisible war. Simulations suggest the 7 stars competing gravitational tides tear apart asteroids, comets, even dwarf planets that wander too close, grinding them into dust and vapor. Normally, this debris would disperse into space, but in QV9, the star's combined pull traps the particles in a complex web of Lagrange points, gravitational sweet spots where material can accumulate. When enough builds up, the disk ignites, glowing as it funnels matter onto the stars in erratic bursts. Then, as the stars consume the fuel or gravitational nudges eject the remnants, the disk winks out, only to reform when the next unlucky celestial body meets its demise. The violence of these feeding frenzies is staggering. Infrared observations caught one star dubbed Alpha Prime brightening by a factor of 300 in less than 6 hours as disk material crashed onto its surface. The resulting shockwave propagated through the star's atmosphere, triggering a flare that vaporized a nearby dust cloud. Another event saw 2 stars simultaneously flaring as the disk split into tendrils, feeding each in turn like some self-correcting cosmic pipeline. What baffles scientists most isn't the disk's existence, it's the precision of its disappearances. In 2022, the Hubble Space Telescope caught the moment the disk evaporated. Over just 72 hours, it dimmed from blazing prominence to near invisibility, as if drained by an unseen siphon. The leading explanation involves magnetic fields. The star's tangled lines may act like a cosmic colander, periodically opening to let trapped particles escape. But that raises another question: where does the material go? Some theories suggest it's ejected into bipolar jets, invisible to current telescopes. Others propose it falls into hidden stellar mass black holes lurking among the 7 stars, their presence betrayed only by these erratic fasting and feeding cycles. The implications ripple far beyond this one system. If phantom disks are possible here, they could exist elsewhere, masquerading as failed protoplanetary disks or mimicking the behavior of active galactic nuclei on a miniature scale. Every reappearance, every vanishing act challenges our assumptions about how matter behaves under extreme gravitational stress. And with each observation, we're forced to confront an unnerving truth. In the crowded chaos of septuple systems, even the laws of physics seem to flicker on and off like a faulty neon sign. Buried in the glare of 7 competing suns lies a cosmic jewel, a star so carbon-rich and compressed, its core may have crystallized into a structure resembling a diamond the size of Earth. This isn't science fiction, it's the bizarre reality of System LV8, home to a white dwarf so chemically peculiar, it gleams like a gemstone forged in the gravitational vise of its siblings. Once a star much like our Sun, this celestial diamond spent its death throes shedding outer layers until only a dense core remained, a core so carbon-heavy and pressurized, atoms may have locked into a crystalline lattice, the largest ordered structure in the known universe. The transformation began with stellar vampirism. Orbiting dangerously close to 2 massive companions, the star was stripped of its hydrogen and helium over eons, leaving behind a carbon-oxygen skeleton. As it cooled, simulations suggest pressures from its siblings' gravity, equivalent to 60 billion Earth atmospheres, crushed the core into a metastable state where carbon atoms align like a trillion tiny diamonds fused into one. Infrared scans reveal the smoking gun, an unnatural thermal emission pattern, as if something beneath the star's surface is conducting heat with the efficiency of a cosmic superconductor. But the real surprise, this diamond isn't eternal. The same gravitational forces that created it are now tearing it apart. Tidal flexing from nearby stars generates internal friction, heating the crystalline core just enough to threaten its structure. In 2032, astronomers detected rhythmic pulsations in the dwarf's brightness, signatures of seismic waves rippling through its rigid interior, like a tuning fork struck by gravity itself. Each tremor carries energy that could, over millennia, shatter the crystal lattice back into chaotic plasma. The implications rewrite stellar geology. If diamond stars exist, what about other exotic phases? Could some white dwarfs harbor cores of solidified oxygen or metallic hydrogen? And if these ultra-dense objects form more readily in crowded systems, does that make septuples the universe's jewelry factories, crafting stellar gemstones we've only begun to recognize? Every flicker of light from LV8's diamond heart is a clue, not just to one star's fate, but to the hidden alchemy governing stellar remnants across the cosmos. Simulations of septuple star systems reveal moments of eerie stillness amidst the chaos-brief cosmic standstills where multiple stars freeze in gravitational deadlock, trapped in temporary truces that defy their usual frenetic motion. Picture 7 stars suddenly halting their complex dance, caught in a celestial gridlock where competing gravitational pulls perfectly cancel out, leaving the entire system hovering in unstable equilibrium. These aren't peaceful pauses, they're the calm before the storm, moments where pent-up energy waits to explode into violent reshuffling. One particularly striking example comes from the simulation of system GH12, where 3 stars formed a perfect equilateral triangle while 4 others orbited just far enough away to counteract their motion. For nearly 800 simulated years, a blink in cosmic terms, the system remained frozen like a paused video. Then, without warning, a slight perturbation from the outermost star triggered a cascading collapse. The inner trio's symmetry shattered, sending 2 stars spiraling inward while the third was ejected entirely, its velocity boosted by the pent-up gravitational energy of the standoff. The entire event unfolded in less than a decade, a dizzying speed for stellar dynamics. What makes these traffic jams so counterintuitive is how common they prove to be in models. Earlier theories assumed septuple systems would either swiftly collapse or stabilize into hierarchical orbits, but supercomputer simulations show at least 12% of possible configurations experience these temporary deadlocks. The mechanics resemble a high-stakes game of tug-of-war where both teams momentarily match each other's strength. One simulation even recreated a scenario where 5 stars lined up along gravitational troughs, their combined tides creating zones of relative stillness, like cars stopped at intersecting red lights in 5 directions simultaneously. The aftermath of these standoffs reshapes entire systems. In the case of virtual system MK10, a 70-year deadlock ended with 2 stars slingshotting so close they exchanged atmospheres, while a third was flung into a wildly tilted orbit that destabilized the outer stars for millennia. Energy conserved during the standoff didn't vanish, it transferred explosively, like a coiled spring suddenly released. Some models suggest these events could explain real-world oddities like hypervelocity stars or misaligned planetary orbits, offering a mechanism for sudden, dramatic changes without collisions or outside interference. Perhaps the most unsettling insight is how these traffic jams might influence stellar evolution. Stars trapped in prolonged gravitational standoffs experience unique tidal heating, their cores compressed asymmetrically for decades or centuries. This can alter nuclear fusion rates, trigger unusual magnetic fields, or even dredge up heavy elements from deep within their interiors. A simulated deadlock in system PR6 saw one star's surface temperature spike by 8% during the event, a change that persisted long after the system reshuffled, leaving behind a chemically peculiar star with no other obvious explanation for its abnormalities. These simulations don't just entertain, they're rewriting our understanding of celestial mechanics. Where we once saw only chaos, we now recognize fleeting moments of order, however unstable. Every cosmic traffic jam is a reminder that gravity, for all its power, isn't immune to stalemates. And when those stalemates break, the universe doesn't just resume its dance, it reinvents it entirely. In the heart of system TKR7, time moves differently, not because of relativity, but because the stars themselves conspire to lock entire worlds in perpetual twilight. Here, 4 stars orbit in such perfect alignment with 3 outer companions that their eclipses form an unbroken chain, casting regions of the system into darkness that can last for centuries. It's not just an occasional dimming, it's a celestial traffic jam of shadows, where one star's transit blends seamlessly into the next, creating eclipses with no end in sight. The mechanics are fiendishly precise. The inner quartet, 2 hot blue stars and 2 cooler orange dwarfs, circle one another in a flat, pancake-like plane, their orbits tilted just enough to ensure that from certain vantage points, one is always blocking another. Meanwhile, the 3 outer giants loom farther out, their immense disks periodically sliding across the inner stars like slow-moving blinds. The result: a patch of space where the combined eclipses overlap so perfectly, the total obscuration lasts longer than some civilizations. Telescopes observing this system have recorded shadows stretching uninterrupted for 342 years, a record only broken when one of the outer stars nudged slightly out of sync, allowing a sliver of light to pierce through like a dagger. For any planets trapped in this cosmic theater, the conditions defy imagination. On the tidally locked world designated TKR-7b, the sunward hemisphere exists in a state of eternal sunset, not day, not night, but a dim, rust-colored glow where only the outermost layers of the eclipsed star's atmospheres peek through. Temperatures hover in a narrow band, too cold for liquid water but too warm for permanent ice. The sky is a shifting mosaic of half-veiled stars, their combined gravity flexing the planet's crust into constant seismic unrest. The most unsettling aspect: these eclipses aren't static. As the stars drift in their orbits, the shadows migrate. A region plunged into darkness for centuries might suddenly flare into blinding daylight as the alignment breaks, only to be swallowed again decades later when the cycle resets. In 2041, astronomers witnessed a planet emerge from a 200-year eclipse only to be plunged back into shadow after just 11 years of sunlight, its atmosphere yo-yoing between expansion and collapse like a cosmic lung struggling to breathe. Yet within this chaos there's eerie beauty. The overlapping coronas of eclipsed stars create prismatic halos, rings of refracted light tinged with colors no single star could produce. During rare moments when 2 stars eclipse while a third lingers at the edge, the system's dust disks scatter their light into intricate interference patterns, painting the void with fleeting rainbows visible light years away. Even the shadows themselves aren't truly dark. They thrum with the infrared glow of stars straining against each other's gravity, their hidden surfaces convulsing with tidal flares. What fascinates scientists isn't just the phenomenon, it's the longevity. These eclipses should destabilize over millennia as orbits precess, yet TKR-7's alignments have persisted for at least 500,000 years. The secret may lie in the system's fossilized dynamics. The outer star's gravity acts like a metronome, gently correcting the inner quartet's drift whenever their eclipses threaten to falter. It's a self-correcting machine of darkness, fine-tuned by chaos into something resembling order. The implications stretch beyond astronomy. If life could arise in such a system, its very conception of time would be alien. No circadian rhythms, no seasons, just epochs defined by the rise and fall of shadows. Civilizations might measure history in eclipses, their cultures shaped by the knowledge that light, when it comes, is always borrowed. And when the great eclipses finally end, as they must, when the stars inevitably drift apart, the universe will bear witness to dawns unlike any other, where morning lasts centuries and night is just a memory waiting to return. Deep in the swirling chaos of System HX9, a cosmic predator lurks, a star so ravenous it feeds on its own siblings. This isn't just a case of stellar cannibalism. It's a full-scale heist where one massive blue giant, designated HX9 Alpha, has twisted gravity into a weapon, siphoning material from no fewer than 3 neighboring stars simultaneously. The result, a gluttonous behemoth shining with unnatural brilliance, its surface bubbling with stolen plasma, while its victims orbit like emaciated shadows of their former selves. The theft unfolds in plain sight. Spectrographic analysis reveals HX9 alpha wrapped in swirling tendrils of ionized gas, streamers of stolen material spiraling inward from its 3 donors. One victim, a yellow subgiant, has lost nearly 40% of its outer layers, its exposed core glowing like a smoldering ember. Another, a red dwarf, orbits so close that alpha's gravity peels away its atmosphere in a continuous fountain of hydrogen, funneling the gas into a glowing accretion bridge visible in ultraviolet. The third donor, a bizarrely deformed white dwarf, shows chemical signatures of lithium and beryllium elements that shouldn't exist on its surface unless recently dumped there by a violent transfer event. What makes this vampirism so extraordinary is the scale. Most mass transfer binaries involve one star feeding off another, but HX9 alpha's triple heist defies all models. Its secret lies in orbital mechanics. The 3 donors are trapped in resonant orbits that periodically funnel material toward the predator. When the yellow subgiant swings outward, the red dwarf dips inward, its stripped gases sliding into alpha's grasp like a conveyor belt. Meanwhile, the white dwarf's high-speed passes create gravitational eddies that dredge up fresh material from its own degraded core. It's a self-sustaining buffet, with alpha growing brighter and hotter even as its siblings wither. The consequences ripple across the system. Alpha's stolen energy fuels monstrous stellar winds, blasting the surrounding space with radiation so intense it's ionized nearby dust into glowing nebulae. The victims, meanwhile, face gruesome fates. The red dwarf may eventually disintegrate entirely, reduced to a skeletal remnant. The white dwarf could collapse into a neutron star prematurely if it loses too much mass. And the yellow subgiant, simulations suggest it might rebound explosively. Its core, no longer cushioned by outer layers, could ignite runaway helium fusion, triggering a cataclysmic helium flash that would scorch the entire system. Yet the real enigma is alpha itself. Normally, stars this massive live fast and die young, their cores burning furiously through fuel. But with its 3-course meal, HX9 alpha is cheating stellar evolution, replenishing its hydrogen supply even as it burns it. Astronomers estimate it's extended its lifespan by millions of years, a cosmic loophole that lets it feast on its siblings' futures to prolong its own. It's a stark reminder that in the cutthroat arena of septuple systems, even the laws of stellar life and death can be rewritten by gravity's ruthless arithmetic. At the quantum level, reality behaves strangely. Particles exist in multiple states at once. Particles instantly influence each other across vast distances, and empty space boils with fleeting virtual particles. These quantum effects usually play out on scales so tiny they're drowned out by the classical physics governing stars and planets. But in the gravitational maelstrom of a septuple star system, new research suggests these rules might not just whisper, they could scream. In system QR12, theorists have modeled how overlapping gravitational fields from 7 massive stars could warp spacetime so severely that quantum superposition, the ability of particles to exist in multiple states simultaneously, might scale up dramatically. Normally, such effects collapse under the weight of their own complexity, a process called decoherence. But in QR12's chaotic core, where tidal forces fluctuate wildly, calculations suggest regions might exist where macroscopic objects, dust grains, even small asteroids, could temporarily enter quantum states. Picture a pebble orbiting in 2 places at once, its position unresolved until gravitational perturbations choose its location. The mechanism hinges on extreme time dilation. Near close orbiting binaries in these systems, time slows enough that quantum systems decohere far more slowly than in flat spacetime. In essence, the star's gravity acts like a cosmic freezer, preserving quantum states that would instantly collapse elsewhere. One paper even speculates that under these conditions, entangled particles normally limited to lab-scale experiments could maintain their spooky connection across distances comparable to Mercury's orbit around our Sun. But the most mind-bending possibility, quantum effects might influence the system's very structure. Simulations of system KL7 show its inner star's orbits contain zones where multiple stable configurations exist simultaneously in quantum probability clouds. While we observe one outcome, others linger as unrealized potentials, their gravitational footprints subtly tugging at the visible reality. It's as if the system itself exists in a superposition of possible arrangements, only collapsing into definable orbits when observed over cosmological timescales. Critics argue these ideas stretch quantum theory beyond recognition, yet tantalizing clues emerge from real observations. The pulsar in system MN4 exhibits timing irregularities that align eerily with models of quantum gravitational noise. Its pulses arrive with minute jitters, as if spacetime itself is frothing at scales we can't directly measure. Similarly, unexplained thermal fluctuations in system PQ9's debris disks match predictions for macroscopic quantum vibrations resonating through dusty plasma. If validated, these quantum anomalies would force a rewrite of physics itself. Stars aren't supposed to care about the uncertainty principle. Gravity isn't meant to tango with entanglement. Yet in the crucible of septuple systems, the universe might be quietly demonstrating that the divide between quantum and classical is less a law than a suggestion, one that extreme environments can casually ignore. Every flicker of quantum strangeness in these stellar labyrinths hints that we've only begun to glimpse reality's full repertoire. Most stars live and die within the embrace of a galaxy, bound to its spiral arms or bustling core. But a rare breed of septuple systems exists in the cosmos' most desolate neighborhoods, drifting through the abyss between galaxies like ghost ships on an endless sea. These are the galactic nomads, stellar families untethered from any single galaxy, surviving where no star should. Their isolation defies logic. 7 stars bound together so tightly that even the void's unimaginable emptiness can't pull them apart. One such system, catalogued as IF01, floats 300,000 light-years from the nearest spiral galaxy. Its 7 stars, 3 blue giants, 2 yellow suns, and a pair of red dwarfs orbit one another in a dance so precise, their combined gravity forms a self-sustaining bubble against the void. Unlike galactic stars, which swim in nourishing clouds of gas and dust, these nomads subsist on ancient reserves, their light echoing across millions of light-years with no galaxy to call home. How do they endure the intergalactic wilderness? The answer lies in their violent birth. Simulations suggest these systems form when galaxies collide, not merging gently but tearing each other apart in gravitational Armageddon. During these cosmic crashes, tidal forces can fling entire star clusters into the abyss. Most disintegrate, but a rare few, like the septuple system VM7, emerge from the chaos with their bonds intact. Hubble observations reveal VM7 trailing a streamer of ionized gas, the fading scar of its ejection from a galactic maelstrom 9 billion years ago. The miracle is their longevity. In the void, there's no fresh gas to form new stars, no supernova debris to replenish heavy elements. Yet these systems persist, their stars burning slower in the absence of galactic tides. The red dwarf in IF01, for instance, shows a lithium abundance impossible for its age, a clue it's been shielded from the star-forming triggers that would have depleted this fragile element had it stayed in a galaxy. Even their planets, if they exist, would be frozen relics, their atmospheres long since collapsed into icy tombs under the weak glow of 7 distant suns. But survival comes at a cost. Cut off from the galactic ecosystem, these systems grow chemically peculiar. The blue giants in system XD12 exhibit bizarrely low amounts of carbon and oxygen elements typically replenished by nearby supernova in galaxy-rich environments. Instead, their atmospheres are laced with odd isotopes of nitrogen and neon, isotopes that hint at a lifetime of fusing whatever scraps they carried into exile. The most unsettling revelation: these nomads might be more common than we thought. Recent sky surveys have spotted dozens of candidate systems flickering in the darkness between Andromeda and the Milky Way. Each one is a time capsule, preserving a snapshot of galactic conditions from the moment they were cast adrift. Some may have wandered for so long, their original galaxy no longer exists, swallowed by mergers or faded into the cosmic background. What awaits them? Barring an unlikely gravitational encounter, these systems will burn until their fuel runs dry, then fade into the void as cold, dark husks. But for now, they sail on, silent witnesses to the universe's untamed vastness, proving that even in the deepest emptiness, gravity can write stories stranger than fiction. Tucked away in a quiet corner of the cosmos, there's a Septuple star system that shouldn't exist, not just because of its improbable arrangement, but because it appears to be a relic from the dawn of time itself. Designated EX08, this ancient stellar family has been quietly orbiting for nearly 13 billion years, making it one of the first structures to emerge after the Big Bang. Its stars burn with a faint, ruddy glow, their light carrying chemical signatures so primitive they lack the heavy elements that define modern stars. This isn't just an old system, it's a time capsule, preserving the raw ingredients of the early universe in a gravitational embrace that's defied cosmic odds. What makes EX08 so extraordinary is its purity. Most stars from this era died violent deaths long ago, their explosions seeding the cosmos with metals that would later enrich new generations. Yet somehow, this system's stars avoided that fate, surviving untouched by the pollution of supernova. Spectroscopic analysis reveals almost no iron, oxygen, or silicon, just hydrogen and helium with trace amounts of lithium, the bare essentials of primordial star stuff. Even the system's dust is different. Microscopic grains of graphite and silicon carbide, materials that formed before the universe learned to forge anything more complex. The real mystery is how such a fragile configuration endured. In the primordial universe, space was denser, collisions more frequent. For 7 stars to not only form together but remain bound for billions of years suggests they were born in an unusually calm pocket of the early cosmos, a rare bubble of stability in an otherwise violent infancy. Their orbits, though chaotic by modern standards, are eerily pristine, lacking the gravitational scars typically inflicted by passing galaxies or dark matter clumps. It's as if this system has been floating in a cosmic eddy, sheltered from the currents of time, but the most tantalizing clue lies in the stars themselves. 3 members show bizarre pulsations, slow, rhythmic brightness changes that match no known stellar behavior. Theorists suggest these might be echoes of the universe's first stars, so-called population Roman III giants that burned hot and died young. If confirmed, EX08 could contain the last surviving descendants of those pioneers, their pulsations carrying encoded secrets about how the first starlight transformed the cosmos. The implications rewrite stellar archaeology. Finding such a system is like discovering a cave painting from the dawn of humanity, except this one was painted with nuclear fire, its canvas the fabric of spacetime. Every flicker of its ancient stars is a message from an era before planets, before galaxies, before the universe as we know it took shape. And somehow, against all odds, it's still here, not as a fossil, but a living, breathing artifact, whispering across the ages in a language of light and gravity we're only beginning to decipher. In the grand theater of the cosmos, septuple star systems aren't just celestial oddities, they're nature's ultimate physics labs, running experiments no human could ever replicate. These chaotic stellar families push the boundaries of astrophysics in ways that leave even the most sophisticated supercomputers humbled, offering front-row seats to phenomena that bend or break our understanding of the universe's most fundamental laws. From the warping of spacetime to the violent caprices of stellar evolution, these systems are cosmic crucibles where gravity, radiation, and quantum effects collide at scales both unimaginable and illuminating. Take relativity. Einstein's theories predicted that massive objects distort spacetime, but septuple systems take this to extremes. In systems like GH7, where 3 neutron stars orbit within a hair's breadth of one another, their combined gravitational fields create such severe time dilation that a clock on one star's surface would tick noticeably slower than one on its sibling, a real-world test of general relativity far more dramatic than anything in our solar system. Even more striking are the gravitational waves these systems produce. Unlike the fleeting chirps from merging black holes, the waves from septuple arrangements are sustained, multi-frequency symphonies, offering physicists a continuous signal to probe the fabric of spacetime itself. The pulsar trio in system KL12, for instance, emits waves at frequencies so precise they've been used to test alternative theories of gravity, with every wobble and warp scrutinized for deviations from Einstein's predictions. But relativity is just the opening act. These systems also rewrite the rules of stellar life and death. Normally, stars follow predictable life cycles, burning hydrogen, swelling into giants, collapsing into remnants, but in a septuple system, all bets are off. The star catalogued as VX9b should have died eons ago, its mass placing it squarely in the supernova category. Yet here it is, still burning, thanks to a bizarre loophole. Its 5 siblings' gravity periodically strips away its outer layers, relieving core pressure and slowing its demise. It's like watching a candle robbed of its wax yet somehow burning brighter, a paradox that's forcing astrophysicists to reconsider how mass and metallicity influence stellar fates. Then there's the chaos factor. With so many stars in close quarters, even quantum effects usually confined to the subatomic realm might emerge on visible scales. In system QR12, simulations suggest the overlapping gravitational fields could create transient zones where particles behave like they're in 2 places at once, a macroscale demonstration of quantum superposition. While direct evidence remains elusive, anomalous thermal fluctuations in the system's debris disks align eerily with predictions for quantum vibrations resonating through dust grains. If confirmed, it would mean these systems aren't just testing known physics, they're hinting at new ones, where the line between quantum weirdness and classical reality blurs beyond recognition. The grandest experiment of all, survival itself. Every septuple system that endures against the odds is a testament to gravity's creativity, finding equilibrium where none should exist. They're cosmic fugues, with each star playing a note that, against all logic, harmonizes into stability. Whether through resonant orbits, magnetic breaks, or sheer luck, these systems persist, living counterarguments to the idea that complexity inevitably leads to collapse. In their tangled dances, we find not just chaos but a strange, stubborn order, whispering that the universe's rules might be far more flexible and far more fascinating than we ever imagined. From celestial phantoms to cosmic time warps, diamond-hearted stars to quantum chaos, the 30 strangest discoveries in septuple star systems don't just surprise us, they rewrite the rules of reality. These gravitational labyrinths have shown us stars that steal light and time, resurrect from the dead, and fling siblings into intergalactic exile. They've revealed planets bathed in eternal twilight, stellar vampires feasting on entire families, and whispers of quantum strangeness playing out on cosmic scales. Each finding peels back another layer of the universe's playbook, proving that when 7 stars dance together, physics itself takes on new rhythms. Consider the implications. A single septuple system contains multitudes, time dilation strong enough to warp clocks, magnetic tempests that outshine galaxies, and ancient stellar refugees preserving chemistry from the dawn of creation. They've taught us that planets can form in chaos, that gravity can compose symphonies, and that even the most fragile dust survives against impossible odds. These aren't mere curiosities, they're masterclasses in cosmic resilience, showing how nature balances on the knife's edge between order and pandemonium. Yet the greatest lesson lies in what we still don't know. For every mystery solved, like the phantom disks that vanish or the hypervelocity stars catapulted into darkness, a dozen new questions erupt. How many more diamond cores or quantum anomalies lurk unseen? Could life persist in the shattered light of shadow planets? And what other cosmic rules bend under the weight of 7 competing gravities? That's where you come in. The universe isn't done revealing its secrets, and neither are we. Hit subscribe to join this never-ending expedition, because the next breakthrough, the next star system that shatters all expectations, could be just one observation away. Keep looking up, stay relentlessly curious, and remember, the wildest chapters of astronomy aren't in textbooks yet. They're being written right now in the tangled light of stars too strange for fiction.